For nearly 40 years, everything we thought we knew about Uranus was built on 6 hours of data. That's it. 6 hours collected by a single spacecraft during a single flyby in January of 1986. No mission has been back since, and it turns out that in those 6 hours, something strange happened. Something that may have quietly corrupted our entire picture of one of the strangest planets in the solar system, without anyone realizing it for decades. Now the James Webb Space Telescope has turned its instruments toward Uranus, and what it's finding doesn't just add new details. In some cases, it's forcing scientists to reconsider whether the old data can even be trusted at all. To understand why that matters, you have to go back to Voyager 2 and the strange planet it found waiting at the edge of the solar system. Uranus is already the oddball of our solar system before you even get to the mystery. Every other planet spins roughly upright, like a top, with its axis pointing more or less perpendicular to its orbit. Uranus doesn't. It rotates almost completely on its side, tilted more than 90 degrees, so that at times its poles, rather than its equator, point directly at the sun. Nobody knows for certain why. The leading explanation is a colossal collision, likely with an object several times the mass of Earth, sometime in the planet's early history, though this remains a hypothesis rather than a settled fact. Whatever knocked Uranus onto its side also dragged its moons and ring system along with it, so that the entire system orbits like a bullseye, tipped over on its edge rather than a disk seen face-on the way Jupiter's or Saturn's systems appear from Earth. That sideways geometry means Uranus experiences seasons unlike anything else in the solar system. Each pole spends the equivalent of 21 Earth years in continuous daylight, followed by 21 years of uninterrupted darkness, as the planet slowly completes its 84-year orbit around the Sun. When Voyager 2 sailed past this tilted, ice-blue world in January of 1986, it became the only spacecraft in history to ever visit it up close. What it measured over those 6 hours has shaped scientific understanding of Uranus ever since. And what it found was deeply strange. The flyby itself was a triumph of engineering. Voyager 2 had already been flying for nearly 9 years by the time it reached Uranus, having launched in 1977 and swung past Jupiter and Saturn along the way. Communicating with the spacecraft across roughly 1.8 billion miles meant that every command took nearly 2.5 hours to arrive, and every piece of data took the same amount of time to come back. There was no opportunity for a second attempt. Whatever Voyager 2 captured in that narrow window as it swept past Uranus's cloud tops would have to serve as humanity's primary reference point for the planet, potentially for generations, and there was no way to know in advance that anything unusual was happening in the space environment around the planet at that exact moment. Voyager 2 detected a magnetosphere, the invisible magnetic bubble that surrounds a planet and deflects the stream of charged particles constantly flowing from the sun. But this one didn't behave like any other in the solar system. It was lopsided, off-center, and tilted at a bizarre 60-degree angle relative to the planet's own rotation axis. Inside that magnetosphere, Voyager 2 found something that made even less sense. Intensely energetic radiation belts, some of the most powerful found anywhere in the solar system outside of Jupiter, existing inside a region that was otherwise almost completely empty of plasma. That combination shouldn't happen. Radiation belts are usually fed by a steady source of charged particles, often supplied by volcanic moons or an active ring system. But Uranus's magnetosphere appeared to have no such source. It was intense and yet strangely hollow, as if something had drained away the fuel while somehow leaving the engine running white-hot. Compare that to what Voyager 2 found at the other giant planets. At Jupiter, the magnetosphere is enormous and fed continuously by the volcanic moon Io, which spews out roughly a ton of sulfur and oxygen, ions into space every second, creating a thick torus of plasma that powers some of the most intense radiation belts anywhere in the solar system. Saturn's magnetosphere gets a steadier, gentler supply of water ice particles from the geysers of its moon Enceladus. Both of those systems make intuitive sense. An active source feeds an active magnetosphere. Uranus broke that pattern entirely. It had the energetic radiation without any visible source feeding it, a combination that didn't fit the model scientists had built from every other planet they'd studied up close. For almost 4 decades, planetary scientists treated this as simply what Uranus is like. Textbooks described it as the most extreme magnetosphere in the solar system. Some researchers concluded that Uranus's major moons must be geologically dead, since an active moon would be expected to leak material into the magnetosphere, and Voyager 2 found none. The picture seemed internally consistent, even if it was strange, and there wasn't yet a full explanation for why an empty magnetosphere should also be so violently energized. But that wasn't even the strangest part. Buried in that 6-hour dataset was a detail almost nobody thought to interrogate for 38 years, what the solar wind itself was doing in the days right before Voyager 2 arrived. In 2024, A team led by James Jasinski at NASA's Jet Propulsion Laboratory went back and reanalyzed roughly 8 months of solar wind data surrounding the flyby, rather than just the few hours immediately around it. What they found rewrote the story. In the days just before Voyager 2 crossed into Uranus's magnetic environment, the planet had been slammed by an unusually intense burst of solar wind, a stream of high-pressure particles from the Sun far stronger than what typically reaches Uranus. According to the study, this kind of solar wind pressure occurs only around 4% of the time. Voyager 2 happened to arrive at almost exactly the peak of that rare event. Lead author James Jasinski put the timing in stark terms, noting that arriving even a few days earlier would have meant encountering an entirely different magnetospheric environment. The dataset the team examined stretched across roughly 8 months surrounding the flyby, tracking the solar wind's velocity, density, and resulting pressure as Voyager 2 approached. Almost every measurement in that 8-month window showed conditions far calmer than what greeted the spacecraft during its actual approach. Only in the narrow days, immediately preceding the flyby, did the numbers spike to their most extreme levels of the entire period, as though the solar system had, by pure chance, arranged its worst possible moment to coincide with humanity's only close look at this planet. The effect on Uranus's magnetosphere was dramatic. The researchers estimate that the intense solar wind compressed the magnetic bubble surrounding the planet down to roughly 20% of its normal volume, shrinking it from an estimated 28 times the planet's diameter down to around 17 times in the span of about a week. If Voyager 2 had simply arrived a few days earlier, before that solar wind event peaked, it likely would have measured a completely different magnetosphere. That number is worth sitting with for a moment. A magnetosphere squeezed down to a fifth of its usual size isn't a minor adjustment. It's the difference between a wide, sprawling magnetic shield and a magnetosphere pressed so tightly against the planet that its usual structure gets fundamentally distorted. Everything Voyager 2 measured about field geometry, plasma density, and particle behavior was captured while that compression was actively underway. It would be a bit like trying to understand the natural shape of a balloon by only ever examining it while something is actively squeezing it from the outside, which means the extreme, lopsided, plasma-starved magnetosphere that has defined our scientific understanding of Uranus for almost 40 years might not represent Uranus at all. It might represent Uranus caught in an unusual temporary squeeze at almost precisely the wrong, or from a storytelling perspective, the most fortunate possible moment. And this is where the story gets much more complicated because the ripple effects go well beyond magnetic field measurements. If the solar wind had compressed the magnetosphere and swept plasma away, right as Voyager 2 flew by, that would also explain the seemingly contradictory radiation belts. The compression event itself may have temporarily boosted the intensity of energetic electrons trapped inside, meaning what looked like a permanently hyperactive radiation environment might instead have been a brief spike, not a baseline condition. Perhaps most striking of all, the moons that scientists concluded were geologically inactive, based on the absence of plasma in Voyager's readings, might not be dead at all. If the missing plasma was simply blown away by a passing solar storm rather than reflecting a genuine absence of activity, then Uranus's 5 major moons could still be releasing material into space, the same way icy moons around other giant planets do. The authors of the reanalysis were direct about the implications, writing that any conclusions drawn from the Voyager 2 flyby should not be treated as representative of Uranus's normal state. Linda Spilker, who served as one of the mission scientists for Voyager 2 during its planetary tour, and now serves as project scientist for the ongoing Voyager mission, has described the original Uranus flyby as packed with surprises from the moment the data started coming back. Surprises that researchers immediately began trying to explain. For nearly 4 decades, the explanation settled on was simply that Uranus itself must be an inherently bizarre planet. The 2224 reanalysis offers a very different explanation. Not that the planet is inherently bizarre, but that humanity's only up-close look happened to catch it in an unrepresentative moment. The scientific equivalent of judging an entire coastline's weather from a single afternoon that happened to include a hurricane. Think about what that means. For nearly 2 generations of astronomers, an entire planet's magnetic personality and judgments about whether its moons are geologically alive or dead were built on a 6-hour snapshot that may have captured a freak event happening less than 1 week out of every 25. So the natural next question is obvious. If the old data can't be fully trusted, what does Uranus actually look like the rest of the time? That's precisely the gap the James Webb Space Telescope has started to fill, not by flying past the planet, but by watching it patiently from nearly 2 billion miles away. Webb doesn't have the advantage of an up-close flyby. What it has instead is time, sensitivity, and infrared vision far beyond what Voyager 2 carried in 1986. In early 2025, an international team led by Paola Taranti of Northumbria University pointed Webb's IR-SPEC instrument at Uranus and monitored it continuously for 15 hours, nearly a full rotation of the planet, using a specific General Observer program designated 57.3. Rather than a brief pass, this was sustained patient observation, the kind Voyager 2's flyby trajectory never allowed. What Webb detected were faint molecular emissions rising as high as 5,000 kilometers above Uranus's visible cloud tops, deep within. The ionosphere, the layer of the atmosphere where gas becomes electrically charged and increasingly shaped by the planet's magnetic field. By tracking how temperature and ion density changed with altitude across an entire rotation, the team produced the first vertical map of Uranus's upper atmosphere ever made. That word vertical matters more than it might sound. Previous observations of Uranus's atmosphere, whether from Voyager 2 or ground-based telescopes, had mostly captured a flat, two-dimensional view, what the cloud tops looked like from outside, or how bright the planet appeared at different wavelengths. What Webb's 15-hour campaign delivered instead was a layered profile, showing how conditions changed not just across the visible disk of the planet, but with height, climbing thousands of kilometers up through the ionosphere. That's the kind of three-dimensional structure that's almost impossible to reconstruct from a single rapid flyby, and it required exactly the sustained, patient observing time that Voyager 2, moving at tens of thousands of miles per hour, never had the luxury of collecting. That map revealed two distinct, bright auroral bands clustered near the planet's magnetic poles, along with an unusual band of reduced emission and lower ion density sitting between them, a feature the researchers link to transitions in the structure of the magnetic field lines themselves. This is the first time scientists have been able to observe Uranus's aurora in 3 dimensions, watching how it shifts and behaves, not from a single passing glimpse, but across sustained observation. Given how strange and possibly misrepresented Uranus's baseline magnetosphere might be, having real, extended, present-day data to compare against the aging Voyager 2 numbers is exactly the kind of correction the field needed. There's a reason auroras matter so much to this story specifically. On Earth, auroras form where our planet's magnetic field lines funnel charged particles down into the atmosphere near the poles, which is why we associate the northern and southern lights with a magnetic field that's relatively simple and well-behaved. Uranus's magnetic field is anything but simple, because the field itself is tilted nearly 60 degrees from the planet's rotation axis, and because the whole planet is already tipped over on its side, relative to its orbit. Uranus's auroras don't stay conveniently parked over fixed geographic poles the way Earth's do. They wobble and shift as the planet rotates, tracing out the genuinely strange geometry of a magnetic field that doesn't line up with anything else about the planet. Mapping that behavior in 3 dimensions, across a full rotation, gives researchers something Voyager 2's brief pass never could. A chance to watch the magnetic field's true shape reveal itself over time, rather than being frozen in a single strange snapshot. But Webb's contributions to the Uranus story didn't stop with auroras and atmospheric structure. In August of 2025, a research team led by scientists at the Southwest Research Institute made 10 separate observations of the Uranian system and discovered something that had been sitting there unnoticed the entire time, a 29th moon. The moon, provisionally designated S25U1, is astonishingly small somewhere, between 8 and 10 kilometers across, according to measurements published following the discovery. Planetary scientist Heidi Hamel, who has studied Uranus for decades, put the scale in blunt terms. An object so small you could plausibly walk around its entire circumference. That tiny size is precisely why it evaded detection for so long. It was too faint and sitting too close to the glare of Uranus's own ring system for Voyager 2 to have ever picked it out in 1986, and too small for Hubble or ground-based telescopes to resolve clearly in the decades since. It's a strange kind of discovery. Not something the moon is doing that defies explanation, but a reminder of just how much of the Uranian system has been sitting in plain sight. Invisible simply because no instrument before Webb had the combination of resolution and infrared sensitivity needed to see it. Consider the scale of what that means. Voyager 2, during its single close pass, discovered 10 new moons in addition to the 5 already known from ground-based observations, along with 2 previously unseen rings. That was already an extraordinary haul for a few hours of observation. But a moon as small as S2025U1, tucked in close to the glare of the rings, was always going to be beyond what a fast-moving spacecraft with 1980s-era cameras could resolve. It took an infrared space telescope, sitting nearly 1 million miles from Earth in a stable orbit, conducting 10 separate observing sessions rather than one hurried pass to finally catch it. The discovery brought Uranus's known moon count to 29, a number that has been slowly climbing for decades as instruments improve. and there's no particular reason to assume it has finished climbing yet. Every earlier estimate of how many moons orbit Uranus, and by extension every model of how its ring system interacts with them, was built on an incomplete inventory. Webb didn't just add a number to a list, it closed a gap nobody previously knew existed. So where does this leave our understanding of Uranus overall? The honest answer is, in the middle of being rewritten. The 2024 reanalysis of Voyager 2's solar wind data doesn't prove that Uranus's magnetosphere is calm and ordinary the rest of the time. That remains a hypothesis, not a confirmed fact, since no spacecraft has been back to check directly. What it does establish is that scientists can no longer treat the 1986 measurements as a reliable baseline. And Webb's long-duration infrared observations are the first real attempt in nearly 40 years to build a new baseline using actual sustained data, rather than a single rushed flyby. Even the auroral structure Webb detected in early 2025 raises its own open question, that unusual dim band between the two auroral zones, tied to shifting magnetic field geometry, hints at complexity in Uranus's magnetic environment that goes beyond simple compression from solar wind, untangling how much of Uranus's strangeness comes from external forces like solar weather, and how much is a genuine permanent feature of a planet tipped over on its side, is still an open problem. The new data hasn't fully resolved. There's also the matter of the moons, which remains genuinely unsettled rather than solved. The 2024 reanalysis raises the possibility that Uranus's 5 major moons could be geologically active, quietly releasing material that would normally show up as plasma in the surrounding magnetosphere. But raising a possibility isn't the same as confirming it. No orbiter has ever circled Uranus long enough to watch its moons for the kind of geysers or surface changes that revealed Enceladus's activity around Saturn. Until something does, the geological status of Uranus's moons remains an open hypothesis, one that the Voyager 2 data can no longer rule out, but also one that nothing currently in orbit can confirm. This is precisely why NASA's own 2023 Planetary Science and Astrobiology Decadal Survey named a dedicated mission to Uranus as one of its top priorities for the coming decade. Not a flyby, but an orbiter, capable of doing what Voyager 2's brief pass through a chance solar storm never could, watching Uranus's magnetosphere behave across weeks, months, and years under both ordinary and extreme conditions, and finally telling us which version of this planet is the real one. A dedicated Uranus orbiter would also settle questions that neither Voyager 2 nor Webb can answer alone. Webb, for all its power, is still observing Uranus from roughly 1.8 billion miles away, limited to whatever wavelengths of light happen to escape the planet's atmosphere and travel that entire distance before reaching its mirrors. An orbiter could sample the magnetosphere directly, the way Voyager 2 briefly did, but repeatedly, across different phases of the solar wind cycle, building exactly the kind of long-term baseline that a single instantaneous measurement can never provide. It could also fly close enough to the major moons to check directly for the plumes or surface activity that would confirm or rule out geological activity, rather than inferring it indirectly from the absence or presence of plasma decades after the fact. Until a spacecraft like that launches, Webb remains our best set of eyes on this tilted, ice-blue world, patiently gathering the kind of long-duration data that a single 6-hour flyby could never provide. What it has found so far doesn't just add new details to the Uranus story, it has quietly pulled the foundation out from under nearly 40 years of assumptions, revealing that maybe we never really understood Uranus in the first place. We just understood one strange week in its life. At the one moment a passing solar storm happened to catch it off guard. The real question now isn't just what Uranus's magnetosphere ordinarily looks like, it's how many other extreme features of the outer solar system, discovered during brief, one-time flybys decades ago, are quietly waiting for a telescope patient enough to check whether they were ever really extreme at all,